The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Rachelle gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm your host, Rachelle. This week we're looking at the atoms and molecules that make up everything around us, from the simplest to the most exotic. Guest host Rachelle Saunders talks to science writer Sam Kean about his new book, The Disappearing Spoon, and other true tales of madness, love, and the history of the world from the periodic table of the elements. But first, let's find out about the cutting-edge research on some of the most advanced man-made molecules in the world. I'm here with Peter Palffy-Muhoray, professor of chemical physics and the associate director of the Liquid Crystal Institute at Kent State University. Peter's areas of expertise include nonlinear optics, pattern formation, and non-equilibrium phenomena in liquid crystals. Welcome to Skeptically Speaking, Peter.
Hello, it's a pleasure to be here.
Now, what are metamaterials, sir?
Well, that's an interesting question. There are a number of definitions that one can come across. I think the most accurate one is that metamaterials are materials whose properties differ markedly from the properties of the constituents, and this is due to a hierarchical structure. I think there's an interesting definition of art by Vladimir Nabokov, who in his book Nikolai Gogol said that art is the brilliant combination of drab parts. And I think one can think of metamaterials along the same lines, that metamaterials are materials that show really exciting new behavior, even though they consist of rather ordinary constituents.
Well, now
so the art of making metamaterials is coaxing novel behavior out of materials that are made up of relatively ordinary things.
Well, the behavior that you're talking about, that's due to the shapes of the material and how it's arranged?
That's right. It's due to the internal structure, which is typically not homogeneous, so there's different kinds of things that make up the material, and the shapes and the composition and the distribution of these various ingredients give rise to this qualitatively new behavior.
So how does one produce metamaterials then?
Well, nature does a pretty good job of it. People tend to think that metamaterials are man-made, but this isn't necessarily so. A good example of metamaterials are bird feathers. So bird feathers are made up of relatively unexciting proteins, beta-carotene, I think, but the color originates from the internal structure, which has pockets of air distributed in a rather special way among the keratin. So it's sort of like a spongy material, and in some cases the spacing of the air and the dielectric protein is really regular, and then you get these brilliant iridescent photonic band gap materials. And in others it's rather soft and subtle. And I think there's a team at Yale, Hu Zhao and Eric Dufresne, who worked on this. And there's a new kind of laser that is coming out based on the structure of these materials. So this is a naturally occurring metamaterial. And of course, people also make materials that are like that are built up of different ingredients. And this can be done either by actually manufacturing, say, by lithography, certain structures. There are a variety of techniques, or it can be done by self-assembly. So there's sort of two fundamentally different approaches that people use.
Well, and there are different kinds of metamaterials, correct?
There are optical metamaterials, and these again can operate in the microwave range to the optical visible light range. But there are metamaterials that are acoustic, for example, and they have a very unusual acoustic behavior. So there's a fairly broad range of metamaterials, different types.
Now, you work specifically with liquid crystals. Tell us about that.
Liquid crystals are really an interesting class of materials. Their key feature is that the constituents are orientationally ordered. And so people tend to think of molecules, God-like molecules, all pointing in the same direction. And these are certainly liquid crystals. But one can also align nanoparticles, and composites of orientationally ordered nanoparticles have really fascinating optical properties. Negative index materials that I'm sure everyone has heard quite a bit about are made up of elements which are anisotropic, and they have to be pointed the right way to make the materials function properly. And so, in some sense, liquid crystals made up of nanoparticles are one really promising class of optical metamaterials.
Well, let's talk about my favorite part of everything always, which is how we can apply this. So what are the things that are being done with metamaterials?
Well, there's really quite a broad range of things. And I think that people often think of metamaterials being used in conjunction with electromagnetic radiation. And so this really ranges then from high-resolution imaging, where it's possible to make structures that can show images with resolution much less than the wavelength of light. And these obviously have really important applications, both in, for example, surveillance, but also in medicine. So if one could make very high-resolution images of body parts, for example, that would be a real advance. So metamaterials are used as efficient sources of electromagnetic radiation and very efficient detectors as well. And so this then opens the door to applications in energy, to collect solar energy efficiently, for example, to convert it into electricity. There's a class of metamaterials which are used for their plasmonic properties. So most of these applications are related to the resonance that these particles have when excited with light of a certain frequency. And these resonances have a lot of interesting both sort of scientific applications and also device applications. But plasmonic particles, and I think that the group of Naomi Hallas at Rice is working on these, that can deliver energy efficiently to very tightly localized regions, so that can be used to deliver energy to tumors, for example. So it goes from sort of medicine to sensors and interesting optical applications, high-efficiency antennas, high-efficiency sources.
There's such a range of things, and one of the things that I'd like to talk about is something that hopefully everybody's heard about by this time, which is the invisibility cloak.
Yes, the invisibility cloak has gotten a great deal of attention. I think that originally the idea came from some applied math people. I think Bob Cohn and Graham Milton originally were interested in guiding sound waves around an object, so there would be no reflection of the sound waves. And they found that by surrounding the object that they wanted to hide, they had to tailor the mechanical properties of the surrounding medium in a certain special way, so that sound waves would be guided around the object rather than into it and bouncing off. And this idea then was extended to optics, and I think Ulf Leonard was probably the person who has really made the field advance a great deal, because he introduced mathematical methods that basically enabled people to determine what the optical properties of the material should be to guide light, to guide the photon current around a particular object, and then recombine it on the other side, so so it looks like there's nothing there.
Now, are we just talking about making things like vehicles, let's say, invisible to radar then?
No, I think ideally one could make them invisible to visible light. So if cloaking were to work well, for example, then you could have, let us say, a wire vertically in front of you, and if you turned on the cloak, as it were, then the wire would simply disappear when you looked at it with ordinary light.
People are actually looking into making clothing out of these kind of materials then.
Well, I think that there are some challenges that need to be overcome, and it's probably important to stress those aspects as well. So whereas theoretically there's tremendous promise, I think there's some formidable challenges that need to be overcome. So basically there are methods to determine what the optical properties of materials should be, of the cloaking materials which hide the object. But to make materials with those properties, I think, is a real challenge. The electric and magnetic response at optical frequencies has to be very precise, and it's just very difficult to simply manufacture that. So I think that's a real challenge that's going to have to be addressed. One of the problems with metallic nanoparticles, which are used today, I think, almost predominantly in metamaterials, are losses, and whereas one can work at microwave frequencies without too many problems, at optical frequencies, losses are a real serious concern.
You're listening to Skeptically Speaking, and I'm talking to Peter Palffy-Muhoray, Professor of Chemical Physics and the Associate Director of the Liquid Crystal Institute at Kent State University. So where do you think that this could go in the future, research into metamaterials? Or I guess a better question is, where do you want it to go?
Well, I mean, that's a hard question. Often I think in science one plans and hopes, and often one stumbles on really unexpected discoveries that then cause the field to explore different areas. I think we need to first of all design materials and then realize them, and I think a lot of it has to be done through self-assembly. I think manufacturing materials by lithography is expensive and slow and painstaking. So I think that self-assembly is one area where we can expect real advances to be made. And exactly how that will work out yet nobody knows, because I think one has to make particles that self-assemble in special ways to give rise to the needed architectures, and then one has to see how they work. And a key notion then is to be able to program the self-assembling particles to create spatially varying structures which may have one kind of internal organization at one point in space, something different somewhere else.
Well, this
but
sounds...
I think it's clear that optical devices will be using these kinds of materials more and more.
Well, it sounds like this is heavily interdisciplinary work.
Absolutely. I think I'm not aware of any other area where input from so many different people is playing a key role. So, on one hand, there are of course the chemists who are absolutely key to making not only molecules but nanoparticles and hybrid nanoparticle chemical composites with very specific structures. We of course have to have physicists who design the optical response. Biologists have had a lot of input because biological materials are often used for self-assembly. So, for example, DNA can be used to form pairs of nanowires with certain resonant properties. Engineers, of course, who will have to make the materials, and applied math people have made really great contributions because modeling, accurate modeling, is absolutely key. So it's a wonderful area in terms of interaction with a broad group of fellow scientists from different areas.
It sounds like fascinating work, and I'm very much looking forward to all the stuff you're doing, and especially an invisibility cloak. I won't lie.
Very good. We hope that there will be some real applications in the near future.
Thanks very much for being here, Peter.
My pleasure. Thank you, Desiree.
If you want to know more about Peter Palffy-Muhoray's work, head to the link on our website at skepticallyspeaking.com. And we'll be right back with guest host Rachelle Saunders and her interview with Sam Kean about his book, The Disappearing Spoon, and other true tales of madness, love, and the history of the world from the periodic table of the elements, after this.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
Hello, and welcome to Skeptically Speaking. I'm Rachelle Saunders, once again delighted to be filling in for regular host Desiree Schell, who will be back behind the microphone next week. My guest today is writer Sam Kean, author and reporter for Science Magazine. In 2009, he was a runner-up for the National Association of Science Writers Award for Best Science Writer Under the Age of 30, and he has been featured on National Public Radio's All Things Considered and On Point. We are here talking about his first book, a New York Times bestseller titled The Disappearing Spoon and Other True Tales of Madness, Love, and History of the World from the Periodic Table of the Elements. Welcome to the show, Sam.
Hi, thanks for having me.
So, Disappearing Spoon is such a massive and compelling collection of historical, biographical, and science stories that I find it really difficult to pick just one spot to begin. But I think the best place would be with the periodic table itself, since that's really the core theme of the book. Can you tell us what was it about the periodic table of the elements that inspired you to collect all these tales?
Well, there were a few things. One of them is that, the periodic table is one thing, if not the only thing, that everyone remembers from high school chemistry class. So it has this really iconic status in science. But at the same time, I knew there were whole swaths of the table that we never got to talk about in class, whole rows of elements that we just never seemed to get to. And I knew there were great stories out there about those elements, stories that people would really appreciate. And I also knew there were some really great stories out there about elements that we all thought we knew really well, but that had sort of a hidden, unusual backstory to them. The other reason I really wanted to write the book is to show people that there's so much more to the periodic table than just the chemistry that you might or might not remember. There's a lot more science on there, certainly, but there's also connections to things like economics and art, wars, poison, so many different areas of life that it intersects with. And I really just wanted to get a story about every single element and put them all together. And that's really how the book came about.
So I understand you had a penchant for breaking thermometers when you were a boy because of a particular fascination with the quicksilver element number 80.
Yes, mercury. That's really how I got my start with the periodic table. I came down with strep throat something like a dozen times when I was 10 years old. And I had to stay home from school each time, of course. And my mother had one of those old-fashioned mercury thermometers that she would put under my tongue. And I admit I was a little clumsy when I was a kid, a little prone to talking to myself. And not infrequently, the thermometer would fall out of my mouth and it would break on our hardwood floor. But my mother was actually very cool about the whole thing. She never, panicked or evacuated the house or anything like that. She actually would get down on her hands and knees with a toothpick, and she would brush the little spheres of mercury together. And I just thought it was the most fascinating substance I'd ever seen, this really gorgeous metal, but it was also a liquid at the same time. And that's really how I got interested in the elements in the first place. And after that, when I started to look into the history of mercury, and I realized what a rich history it had, I got even more excited. It had a very big role in early science, especially science instruments. Alchemists adored mercury, but it has a pedigree going back all the way to classical times. Medicine's another area. Lots and lots of people used mercury as a medicine for a long time. So the combination of the way it looked and the really rich history sort of captivated me.
So you talked a little bit about how your mother would push the little balls of mercury together. Why does mercury act this way instead of kind of pooling like a regular liquid?
Well, mercury is, of course, different. It's a metal, and mercury atoms just prefer to be by other mercury atoms. There are some elements that are very reactive that will go almost out of their way to interact with other atoms and shuffle electrons around. But mercury really wants to stay by itself, and that's the reason why it crouches into little spheres, because a sphere, of course, has the smallest surface area for a given volume. So if it can stay in a sphere, it's exposing as little as possible of itself to the outside world. So that's the basic reason why mercury acts like that.
So I've also heard that mercury played a role in identifying some of the exact locations of Lewis and Clark's campsites, particularly when it comes to pinpointing the latrines.
Yes, it did. This story has to do with a man named Dr. Benjamin Rush. He lived in Philadelphia in the United States. A very prominent physician, very brave actually. He stayed behind once, was known for staying behind during a yellow fever epidemic, helping out a lot of people when other doctors had abandoned them. Unfortunately, his pet treatment for most diseases was sort of this mercury chloride sludge that he would feed people, often until their hair or their teeth started to get loose or even fall out. The idea at the time was that if someone had an ugly ailment, you had to fight it with something even uglier, which mercury certainly brought out those symptoms. But mercury also does something else, and Dr. Rush patented what are called Dr. Rush's bilious pills. And he sent 600 of those pills off with Lewis and Clark when they went through the wilderness. And there's really no delicate way to put it, but the pills were extremely powerful laxatives. They called them thunderclappers. And the idea was that if you ate some questionable food or drank some water you shouldn't have, you would take one of the pills and it would flush you out completely. It would get rid of everything basically that was in your intestines. But the side benefit it's had for archaeologists and historians is that they can actually pinpoint a few places where they know Lewis and Clark must have stayed, and as you said, specifically dug a latrine, because the level of mercury in the soil is just too high for it to have been natural.
Awesome. So everyone knows that mercury is really poisonous, but probably fewer people realize that the element sitting on top of it in the periodic table is also quite dangerous. Cadmium is used today to make rechargeable batteries, but back in the first half of the 1900s, Japan had some problems with cadmium poisoning, didn't they?
They did. It was a very, very sad story, actually. There was a mine who was trying to produce a lot of zinc. Zinc was very important for industrial reasons. And zinc sits right above cadmium on the periodic table, which means, as you know, this is very common across the periodic table, that if two elements sit one on top of the other, they have very similar properties, and they're often found mixed together in deposits in the ground. The miners didn't want the cadmium, though, so they separated it out, and following the pretty lax environmental standards of the day, they just dumped it onto the ground and let it wash away. Unfortunately, there were rice paddies downstream, more at the foot of these mountains, and rice just happens to be sort of a cadmium sponge. It sucks it up right out of the water and concentrates it. And at the time especially, rice was a staple in a lot of these poor farmers' diets. So they were ingesting loads and loads of rice at every meal. And over the years, the cadmium started to build up in their body. And they came down with strange symptoms they'd never really seen before. The disease was called Atai disease, which means ouch, ouch disease, because it was so painful even just sitting around. And the two especially notable symptoms were that people's kidneys started to fail and that they would get extremely brittle bones. There's a story about a doctor actually breaking one woman's wrist just by taking her pulse. That's how delicate and soft her bones were. And it actually took a very long time for people to figure out what was going on. And then when a doctor did finally figure out that cadmium was to blame, he faced a lot of resistance, both from the mine company, which is understandable, but also from local government officials who just wanted to hush the whole thing up. And he really had to fight for a very long time, for a number of decades, to get the case tried in court and to get compensation for these victims. It became a very famous poisoning case in Japan, sort of their version of that book in the movie, A Civil Action. But it did have one unusual effect later, in that cadmium became such a notorious poison that when the Japanese were making a movie later, the latest Godzilla sequel in the 1980s, they actually put cadmium on the tips of the missiles that they used to kill Godzilla in the movie. It was basically the worst thing they could think of, was this cadmium. And considering that an H-bomb, a hydrogen bomb, had given Godzilla life in the first place, that's a pretty dim view of element 48.
You're listening to Skeptically Speaking with Rachelle Saunders, guest hosting for Desiree Schell. We're here today with element aficionado Sam Kean, author of the best-selling book The Disappearing Spoon and Other True Tales of Madness, Love, and History of the World from the Periodic Table of the Elements. Now, the periodic table wasn't always organized the way it is today. The modern layout is generally credited to Russian chemist Dmitry Mendeleev, but like with most scientific breakthroughs, the true tale often contains more characters. What role did German chemist Robert Bunsen play in this story?
Bunsen did a few things. Bunsen, of course, is very famous for the Bunsen burner, everyone's favorite equipment in lab. He actually didn't invent the burner. He just modified it and improved it. But one piece of equipment that he did invent was called the spectroscope. And that proved very, very important in identifying elements on the periodic table. The basic idea that you shine a light on a sample and that the sample then produces its own light. Each element on the table has a characteristic spectrum of different very narrow bands of light that it produces. So basically, you can identify individual elements in a sample. And what that helped people do is eliminate some of these minerals that actually had more than one element in them and figure out what actually were elements and weren't elements. So that was really the start of his contribution. The other contribution he made is that he was a teacher in Heidelberg when Dmitry Mendeleev was there. They didn't get along, actually. They had some significant temperamental differences. Bunsen especially was known for kind of keeping a sloppy lab. He had kind of a rough life in that things were always exploding around him, or he almost lost an eye at one point, whereas Mendeleev was much more careful, much more meticulous. So they didn't get along very well. But Bunsen was a very important influence on Mendeleev, and when Mendeleev went back to Russia and started to put together his periodic system, Bunsen, I think, deserves a fair amount of credit for being an intellectual influence on him.
I also have heard that Mendeleev had a few rivals working on the same problem of grouping elements, including John Newlands in England and I think Julius Lothar Meyer in Germany. How did their research differ from Mendeleev's, and what made Mendeleev stand out insofar as history is concerned?
Yeah, there were actually 6 scientists who came up with something like the periodic table, and Mendeleev was the last one of them. You mentioned a few of the more prominent ones, John Newlands and Lothar Meyer, the German chemist. What they did is they came up with a system that, again, put the elements in certain spots and grouped elements that had similar properties in the same row or column. Mendeleev's work, what it really did was went beyond what those other people had done. Mendeleev had a few advantages over them in that he worked primarily with metals. And if you've ever looked at the periodic table, most of the elements on there are metals, and they tend to look very alike and have sort of similar properties. So Mendeleev's expertise there helped him sort out these subtle differences and put the elements into better spots on the table than the other chemists had been able to. The other thing Mendeleev did that he was very famous for was when he made his columns and rows, he sometimes found that there was a gap where there was no known element that would fit into a certain spot. Scientists just hadn't discovered it yet. But Mendeleev predicted that they would discover it someday. And not only that, he went beyond that and started predicting the properties of those elements and said, this should be its density, it should have a boiling point of roughly this, things like that. And when his predictions started to come true, it was astounding to other scientists that this man who was basically sitting in his lab in St. Petersburg, hundreds of miles away, was able to foresee the properties of elements that hadn't even been discovered yet. And that was really when the periodic table stopped being just sort of a clever arrangement of elements and really became a scientific tool, something that had predictive power and something that really explained deeper features of the elements and how they're organized. So that's why Mendeleev got all the credit he does. I think a good comparison is to Darwin and the theory of natural selection. Darwin wasn't the only one who came up with the idea of natural selection, but he did far more work with it, and he really foresaw a lot more of the consequences. That's sort of the role Mendeleev played.
So, not long after Mendeleev's table came out, one of the elements he predicted was discovered, which I believe also has a lot to do with the title of your book.
It does. The element is gallium. It's an element that sits right below aluminum on the periodic table. And gallium was discovered in 1875 by a French chemist. And he actually, when he discovered it, he published some data about what he thought the density, the boiling point, things like that were. And Mendeleev contradicted him and said, no, I think you may have made a mistake in the work that you were doing, which is a bit insulting for a theoretical person to say to someone. But it turns out that Mendeleev was right. And again, that's the part that sort of astounded people around the world. But it does have something to do with the title of my book as well. So it's an element I enjoy. Again, it sits below aluminum, and so it has very similar properties to aluminum, except that gallium melts at about 85 degrees Fahrenheit, which I think is around 33, 32 degrees Celsius or so. So even if you put it in the palm of your hand, it will start to soften up. It will start to melt there. And the disappearing spoon comes in because it's sort of a classic nerdy science prank to make a spoon out of gallium metal and then to serve it to somebody with hot coffee or tea or something like that. And they, of course, just think they're getting an aluminum spoon. But they figure out something unusual is going on when they put it in their hot coffee or tea and the head of it disappears on them. So, the disappearing spoon.
Science pranks are the best pranks. This is Skeptically Speaking, guest hosted today by Rachelle Saunders, keeping the host seat warm for Desiree Schell until next week. We've got science writer, journalist, and thermometer breaker Sam Kean on the line, author of the book The Disappearing Spoon and Other True Tales of Madness, Love, and History of the World from the Periodic Table of the Elements. So in all this talk about the elements, I feel we would be remiss if we didn't talk about where these building blocks of everything come from. I believe stars have something to do with it, right?
They do. At the beginning of the universe, when the Big Bang happened, from that sort of chaos of little particles and light and everything that emerged from the Big Bang, hydrogen eventually formed, which is the simplest element and the first element out there. There was also a little bit of helium and maybe even a little lithium, which are the second and third elements. But basically you had a big mess of hydrogen that it got blown all across the universe. Eventually, some of that hydrogen started to clump together, and it started to form stars, just like our sun. And inside those stars, deep inside them, things were hot enough and it was dense enough that the hydrogen started to get squished together and form helium, the second element. So you started to accumulate helium. Once stars get a little older, they eventually start fusing other elements together. They start fusing helium to form beryllium, which is the fourth element, and carbon and oxygen, and the elements that we're really familiar with today. And they start fusing more and more together, and that's when you start to get appreciable quantities of some of the more famous and useful elements, at least for human beings, like oxygen, nitrogen, things like that. However, that fusion process deep inside stars can only go so far. Even the biggest, heaviest, hottest stars, bigger than the sun, only fuse atoms together enough to get to iron, which is element 26. After that, it actually takes more energy to fuse atoms together than you get out of the fusion process. So it's energetically unfavorable. To get heavier elements, then, you have to have what's called a supernova. And it's sort of hard for the human mind to comprehend what a supernova is and how big it actually is. It only happens with the biggest, most massive stars, and they collapse from enormous, enormous spaces down to a very small space, and then they explode outward. And it's really hard to emphasize how big these explosions are. They're sometimes brighter than 1 billion galaxies put together. They're just immense, immense explosions. And in that explosion outward, there's sort of this particle blizzard of all these atoms knocking into each other. And that's when you get the elements beyond iron. You get all the elements actually up to uranium, element 92. So you really get a wide variety in a supernova. And the fact that we have elements beyond iron all the way up to uranium on Earth suggests that we do have a supernova in the history of our solar system, maybe even more than one. And so it's a good clue that a supernova might even have triggered the formation of our solar system.
So I want to talk about another really common element, aluminum. This was one of the stories that really intrigued me from your book. Today we use aluminum for everything from pop cans to baseball bats, but once upon a time it was actually considered a precious metal and more expensive than gold. That's a pretty significant price markdown.
Yeah, aluminum is one of those elements whose fortunes have really changed over time. Aluminum is very common. It's the most common metal in the Earth's crust, hundreds and thousands and millions of times more common than gold. But aluminum is always very tightly bonded to another element in the crust, usually oxygen in various minerals. So when scientists in the early 1800s started to get pure samples of aluminum for the first time, it was considered sort of a miraculous metal. It was very light and very strong, but it also had this very nice, attractive shine to it. And that's why they decided to classify it as a precious metal. And as you said, it actually became more expensive than silver and more expensive than gold. In fact, it even became something of a status symbol for world leaders to get their hands on aluminum. The French used to display these Fort Knox-like bars of aluminum next to their crown jewels. And the Emperor Napoleon III had this prized set of aluminum cutlery that he reserved for his most favored guests at banquets. And the lesser nobility actually had to eat with gold knives and forks. And in the United States, where I live in Washington, D.C., on our National Mall, we have the Washington Monument. It's a very tall obelisk on the made of white stone. But at the very, very tip of it, there's actually a 6-inch pyramid of aluminum up there. And it serves two purposes. One, it was a lightning rod. But the reason they chose aluminum is that the United States was kind of bragging at the time and saying that it was such an up-and-coming industrial power that it could afford to put aluminum, of all things, onto its public monuments. Of course, right after that, in the 1880s, after the erection of the Washington Monument, the aluminum market crashed pretty hard thanks to the discovery of a few chemists, one in the United States and a few in Europe, who figured out how to produce aluminum on an industrial scale for the first time. And that's when it really went from the most precious metal on Earth to one of the more passé metals on Earth, but one of the more productive ones. And I think it really depends on your temperament and how you look at the world, whether you think aluminum was better off as this really rare but very precious metal, or something we take for granted nowadays, but that really we probably couldn't live our lives without.
And perhaps you can settle a bit of an argument I've been having. Is it pronounced aluminum or aluminium?
That depends a little bit on where you are. In the United States, where I live, it's aluminum. But I think basically the rest of the world pronounces it aluminium. And that actually goes back to the discovery by the American scientist who helped crash the aluminum market. His name was Charles Hall. And when he started to file for patents on his process and everything, he did say, or he did write in there, aluminium with an extra I at the end. But no one knows quite how it happened. It might be an urban legend. But at some point, a flyer came up. Some people say it was a mistake. Some people say he did it on purpose. But the flyer to advertise his new business said not aluminium, but aluminum on it. And Hall thought it was a really brilliant coinage, partly because it sort of aligned his metal with some of the more classier ones on the table, particularly platinum. He liked the association there between aluminum and platinum. And because of Hall, the spelling of aluminum spread so quickly in the United States that it became sort of locked into our mentality here, and it probably won't ever change. It's like our refusal to switch to the metric system. We have our own ways, darn it, and we're going to keep doing it. But if you're anywhere else in the world, you would have to say aluminium, definitely.
So this is probably a battle I can't win, really.
Not with someone from the United States, probably not.
You're listening to Skeptically Speaking with guest host Rachelle Saunders, standing in for regular host Desiree Schell, who will return to a radio near you next week. Today I've got Sam Kean, science writer and author of the book The Disappearing Spoon and Other True Tales of Madness, Love, and History of the World from the Periodic Table of the Elements. And we'll be right back after this.
On the next episode of Skeptically Speaking, we're discussing evolution and a less well-known bearded scientist who helped to expand the theory. We'll talk to Dr. Lee Allen Dugatkin about his book, The Prince of Evolution, Peter Kropotkin's Adventures in Science and Politics. And science history blogger Michael D. Barton joins us to examine the ways that evolution deniers misuse the words of Charles Darwin to make their case. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, guest hosting today for Desiree Schell. We've got Sam Kean on the line, science reporter and author of the fascinating best-selling book, The Disappearing Spoon and Other True Tales of Madness, Love, and History of the World from the Periodic Table of the Elements. And we're talking about all the many, many ways elements and the periodic table have contributed to and helped shape our history. I'd like to switch gears for a minute and talk about a little-known Austrian scientist named Lise Meitner, who made some pretty big contributions to atomic science in the 20s and 30s, and was one of the key characters behind the discovery of nuclear fission. Can you tell us a little bit about her and her partner Otto Hahn?
Yeah, Hahn and Meitner were two extremely important chemists. As you said, Meitner was Austrian, but she was working in Germany with Hahn in the 1920s and 1930s. And Hahn really recognized what a great scientist Meitner was. Hahn at the time was probably the best chemist in the world, really the top one around. But he recognized that Meitner was very good, his equal in many ways. And he actually was sort of brave in standing up for her. At one point in Germany, women weren't allowed to have their own labs in certain buildings. And rather than just buckle and go with this, Hahn actually moved his lab into a shed behind a building so he could work with Meitner and continue to collaborate with her. Unfortunately for her, Meitner had some Jewish, I believe she had a Jewish grandparent. She had some Jewish ancestors, which of course in Germany eventually became of great liability. And in the late 1930s, she actually had to flee and ended up in Sweden, sort of isolated from the scientific community. Meanwhile, though, there was some really important work going on with what were called the transuranium elements. They were erroneously called that. A scientist named Enrico Fermi in Italy thought he had discovered how to make elements bigger than uranium. That's why they're the transuraniums. Unfortunately for him, this turned out to be wrong. And Hahn was the first one to realize that something unusual was going on. He was doing some chemistry work on these supposed transuraniums, and he noticed that they just weren't behaving like they should. They were behaving a lot actually like elements in different rows and places on the periodic table, and he just couldn't figure out what was going on. So eventually he sort of snuck to Copenhagen and had sort of an illicit rendezvous with Meitner there, who snuck back in to that part of Europe so they could work on this problem. And Meitner was the first one to realize that these weren't transuranium elements. They were actually smaller elements that had emerged when the uranium atom split into two. It was nuclear fission that they were seeing. And again, she was the first one to realize what had happened and the implications for what had happened. For various reasons, mostly because of Meitner's status, being Jewish and a woman, they decided that Hahn would publish this work and get it out there because he could do it very quickly. Unfortunately, later on in the war, as it became clear that this work on uranium fission was very, very important and was going to have enormous consequences, no one really was giving credit to Meitner for this because they really didn't understand what she had contributed. And when they finally awarded a Nobel Prize for this work, they gave it to Hahn by himself. And despite all that he'd done for Meitner before, sort of to his shame, Hahn kept quiet about everything, and he didn't point out the contributions Meitner had made, and ended up sort of stealing the glory just for himself. And Meitner never did win her Nobel Prize in the end. She died without one.
Now, I understand she actually ended up, perhaps by some standards, winning in the end. Isn't she memorialized on the periodic table somewhere?
She is indeed, and that's really how I look at it in the book. Hahn, again, won the Nobel Prize, but element 109 eventually got named after Meitner. It's called meiternnium. And in some ways, that's really a bigger and better honor than winning a Nobel Prize. For one thing, there are far fewer elements than there are Nobel Prize winners, and the discrepancy grows more and more each year. And people really don't remember a lot of the Nobel Prize winners, except for maybe a few of them, whereas the periodic table is something that people get exposed to year after year, and that will really last until the end of our civilization. So, as you said, she really did, in some ways, win out at the end, even if it was too late to console her while she lived.
Moving on from scientists that get shortchanged, let's talk a little bit about elements that get shortchanged by history. Of course, everybody has heard of Silicon Valley, but probably very few people realize it might just as easily have been called Germanium Valley.
Germanium Valley, yes. It's sort of a no-luck, sad story element, germanium. It, again, sits right below silicon on the table, and so it has very similar properties. And two of the most important pieces of electronics in history, the transistor and the integrated circuit, were both invented with germanium as the main component. Germanium had some advantages over silicon, especially the fact that it was easier to get pure samples of germanium. Silicon is the element in sand, of course, and it's very common, but it's very hard to get pure samples. It's often contaminated. So when they needed to do the really important fundamental work in the 50s and 60s, they turned to germanium and used that element. Unfortunately for it, the lure of silicon eventually became too much. It was just too cheap, and eventually it did replace germanium in basically all forms of electronics, and that's why we call it Silicon Valley today and not Germanium Valley.
There's another really interesting story that I remember reading from your book, and it's actually about a very peculiar gold rush that happened quite a ways back.
Yes, the element in question here is the element tellurium, element 52. It's a pretty obscure element, doesn't really have a whole lot of use, has some unusual properties, but pretty much an obscure element. The one thing it does, though, is that unlike any other element on the table, tellurium will form a chemical bond with gold. Gold can be mixed with other elements and alloys and things like that, but no other element will form a bond with gold. Tellurium's the only one that will. And when tellurium does this, it forms sort of this yellowish compound. It looks, in fact, a little bit like fool's gold, even though there really is gold in it, unlike with fool's gold. And this led to that unusual gold rush in Australia in the 1890s and very early 1900s. There was a big gold rush. People came from all around, and not too long after they got there, they had basically picked all of the easy sources of gold clean. There really wasn't any gold left. Unfortunately for them, they didn't realize that there was actually a fair amount of gold still left over bonded to tellurium. It just looked to them like fool's gold or something else, and so they were throwing whole rocks of this rubble away, just tossing in refuse heaps. Or what was really interesting was the people who decided to take these rocks, then grind them up and use them as mortar and, fill in potholes in their streets or build chimneys for their homes with them, things like that. Eventually, word got out about what was happening and the fact that there was actually gold in what they thought was refuse. And it wasn't too long before some of these hard-luck miners were out in the middle of the street with pickaxes, remaking the potholes or knocking down their own home and hearth to get at that gold inside the tellurium minerals. So I ended up calling it the Fool's Gold Rush, since it was sort of a double negative kind of thing. They were a little too clever for their own good there.
That is a very excellent name. The periodic table also contains a few surprises, including one seemingly misplaced element called bismuth. What is it that makes bismuth and its placement unique in the periodic table?
Well, there's a little row of elements. I like to call it Poisoner's Corridor. Down there you have mercury, you have lead, you have polonium, a lot of elements that are really, really dangerous. Oh, there's also thallium, which is probably the most deadly element, atom for atom, on the periodic table, element 81. And in bismuth's column on the periodic table, there's also arsenic and antimony, two other pretty toxic elements. But bismuth itself, for whatever reason, is not only not toxic, in some ways it's actually medicinal. It's the biz in Pepto-Bismol, what soothes your stomach. And so for all of its disreputable neighbors, right there in the middle of all of them, you have bismuth, which is actually, again, medicinal. It's in some ways good for you. So I call it the most misplaced element on the periodic table. You just wouldn't expect, looking at all its neighbors, that it could have those properties, but it does.
Now, there was actually an experiment in France in, I think, about 2003 that featured quite a lot of bismuth and quite a lot of patience. What were those physicists in France trying to determine with this element?
They were trying to determine whether bismuth is a stable element or not. There are certain elements, especially the very heavy ones, uranium is most famous, that split apart into smaller atoms. There are many smaller atoms that don't split apart and that won't ever split apart. They're stable atoms. And these scientists were trying to determine whether bismuth was a stable atom or a radioactive atom that would eventually fall apart. And they knew bismuth was pretty stable. They knew that it wasn't one of those elements that falls apart quickly, but they couldn't tell if it actually went radioactive or not. So eventually, as you said, they got a big pile of bismuth together and put detectors around it, very sensitive detectors, and just sat around and waited to see if the bismuth would go radioactive. They waited years and years and years, and eventually they did discover that bismuth will go radioactive. Its elements have a half-life of, I can't remember how many zeros it has. It's something like 10 to the 18th zeros. I remember that if you take the age of the universe and multiply it by itself, you basically get the half-life of a bismuth atom. But it will go radioactive at some point. So if the universe ends up lasting, forever and ever, all of the bismuth atoms will one day disappear, but none of us are going to be around to see it, that's for sure.
So we don't really have to worry about running out of Pepto-Bismol anytime soon then?
No time soon. We will be long gone and forgotten by then.
Sam, I would love to keep adventuring across the periodic table with you today, but unfortunately we are all out of time. Thank you so much for being here.
Oh, well, thanks for having me.
You can find out more about Sam Kean and his book, The Disappearing Spoon, and other true tales of madness, love, and history of the world from the periodic table of the elements by visiting samkean.com, a link you can find in our website, skepticallyspeaking.com. While you're there, please do keep clicking and check out our Facebook page and Twitter feed, or click on over to iTunes where you can download past episodes, subscribe to the show, or leave a review. Thanks for listening. Regular host Desiree Schell will be back behind the wheel next week on Skeptically Speaking.
One last thing. A new blog has sprung up that I'd like to mention. The Doubtful News blog. If you need a one-stop shop for current news stories on things like ghosts, cryptozoology, UFOs, alternative health, and as the blog creators put it, weird stuff like that, you should check it out. This is definitely not a straight science story site. It's all odd, all the time, but from a skeptical perspective. And if you find an interesting news story that could benefit from an evidence-based lens, perhaps, you can send it in. Head to doubtfulnews.wordpress.com because, as the site says, people really believe this stuff.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, break the spell of Pavlov's spells. Cause we're skeptically speaking, our mind reading tarot cards and witches, psychics, and their spoon bending finding mind tricks. All the humbug, flim-flam, frauds and shams, the charlatan woo. I don't think you understand. It's the hocus pocus, out of focus locus, eroding the brain, making gains on the hopeless. Let the crystal ball fall, smash on the floor. Leave the pieces alone, we don't need them anymore. Just a microscope, telescope, magnifier, reading in between the lines of these lies. Bring it on, the skeptics await your letter, your call, tweet, homing, pigeon, whatever. Desiree Shell gonna raise a little hell, metaphorically that is, cause we're skeptically speaking.
Skeptically Speaking is produced with the support of CJSR 88.5 FM in Edmonton, Alberta, Canada. Our studio assistants are Brent Kelly and Rachelle Saunders. Ryan Bromsgrove is our studio technician and research assistant. The show is produced and edited by K.O. Myers. Our theme song was written and recorded by AOK. And I'm your host, Desiree Shell.